Omitted variable bias is probably one of the more difficult things that we are looking into in this course. So what is omitted variable bias, and how could we quantify it? We are going to look into that in this video. So far, we have talked about the simple regression, where we have one x variable explaining a y variable. So we have one process depending on one other process. This is not very realistic in real life, so we need more variables to explain our y variables. Okay, so what we have, if we only look at the simple regression line, is that we have this y variable. It's dependent on the intercept and the slope times one other variable, the x1. This means that if you have the regression slope, the y hat, then the equation contains all factors. The residual contains all factors that affect y, but are not contained in y or in the x variable. But if you look here, we are talking about the population regression. Okay, the true relationship between the x variable and the y variable. Okay, and I was looking in the book, and I think we need to explain this in a bit different way, such that if you look at the population regression, for example, you have the y here, and you have the x1 here, and you have the x2 here. Okay, bear with me. You know that the intercept is just the population intercept, and if you have some data going up here, okay, let's say this is the population data, sorry about that, then to get this population regression line, let's call that the population regression line. Okay, so this is the population regression line. These residuals are whatever is not explained in y by x1 and x2. Okay, so for example, we have that x1 has this effect on y, which means that this slope is the population slope beta 1, okay? The true slope, right? Which means, sorry about that, I have to do like this. It's like this, okay? This is the and we do like this, okay? This is the intercept. This is the true slope for the effect of the x1 variable on the y variable, okay? The second effect is the effect of x2, right? So this line is parallel to this line, right? Okay, these are parallel. So this would be the change in y given a change in, or related to a change in x2, right? So what you do is that you add the intercept, and then you add the effect of an increased x variable, right? And then you add the effect of an increased x2 variable, right? Okay, so which means that if you only, this is the population regression line with y equals the true intercept plus the true beta 1 times x1 plus the true beta 2 times x2, right? Okay, so we see that if you only have x1 in the regression, then the data is really slow, right? Which means that if you only have the true parameter in this regression equation, then you would have these, this is the data, right? But if you only include the beta naught and the x1 variable, then you would have these residuals. And you see, in our case, these residuals, they are large when beta is large, and they are small when beta is small. So in this case, if we do not include the beta 2 or the x2 variable, then we would have correlation between the x and the residuals. Okay, and remember that correlation is positive when you have two downward sloping lines or two upward sloping lines, and correlation is negative when these data sets or these lines are crossing. One is downward sloping and one is upward sloping. Okay, so with that in mind, we can continue, and you can see that correlation between the residuals and the x variable here, the x1, can be positive or negative depending on the effect the other variable has on the data, on the y variable, and on x1. Okay, the correlation between x1 and x2. But let's move on. Okay, so we have this population population regression, okay, the population regression. So if you only contain or include x1 in your regression, then the residual contains all factors that affect the y but are not contained in the x1 variable. Okay, so if we would like to understand the true relationship between y and x, which means that we would like to understand, we would like to find beta 1, okay, the true beta, or an estimate of the true beta, then we want to get an unbiased estimate of beta 1, which means that on average we are on average we are hitting the true beta. So if we estimate the simple regression model, then often we would get a biased estimate, since there is a correlation between x1 and the residual, because there is some other process, some other x, which affects the y variable and is correlated with the x1 variable. Okay, so if the correlation between our x1 variable and the residual is different from 0, then this is from running a regression, of only y equals to beta naught plus beta beta 1 minus x1 minus sorry, we have it here. So okay, and these are brackets. Okay, so okay, so if we run the regression with only, or we look at the regression with the population slope, then and we get a non-zero correlation, then we know that the expectation of the residual given a level of the x1 variable is different from 0. And you can see that from our line here, or our plot, that if in this case, if x1 has a high value, then the residual also has a high value. Okay, if the x1 variable has a low value, then the expectation of the size of the residual is lower. So there is a correlation between these the x and the residual, which means that the conditional mean of the residual is different from 0. So this means that the first least squares assumption is violated, and we need that to obtain a unbiased estimate of our sample slope. Okay, our sample slope, the beta 1 hat. So if there is correlation between the residual and the x, the true x variable, we would get a biased estimate of the sample slope. Okay, and in practice, one way in which the correlation might be non-zero is due to omitted variable bias. And omitted variable bias happens if you have have an x variable which is correlated with the x variable in your model, and in addition, this accounted for x variable is relevant for explaining the y variable, which means that it has a non-zero slope. So this means that beta 2 is different from 0. Okay, so and this means that the correlation between x1 and x2 is also non-zero. So if we omit the x2 variable from the regression, but it should have been in the regression, then the x2 variable gets absorbed in the population residual u, right? So and because x1 and x2 are correlated, this means that the residual, the population residuals, and x1 are also correlated, which means that the first least squares assumption is violated, and we will get a biased estimate of beta 1. So, for example, suppose that we have this true population regression mode for returns to schooling, which is here. The returns is measured by the wage level, and this wage level is explained in the population by the slope, the coefficient times the education level in years, and a coefficient times a certain ability. Okay, so and plus a certain residual which contains all other factors which affect the wage level, which is not accounted for by education and ability. So what if we assume that the expectation of the residual, given the level in education and the level of ability, it's equal to 0, which means that if you can account for the education and the ability, then you will get unbiased estimates of the wage. So to get an unbiased estimate of the slope on education, right, we would collect data on wages and education and ability for a simple random sample of individuals. So that would mean that we would have a data table which is wages, it's education, and it's ability. So then we would have a simple random sample, but ability is an unobservable trait, right? So we do not have this data, which means that we still go on with our analysis, but we estimate our simple regression model with just wage and education. But remember that the true population regression was wage plus beta naught plus coefficient times education plus coefficient times ability plus a residual. Now our residual in this case contains both ability and the original unbiased or uncorrelated residual. Okay, so if we regress this simple regression model, we regress wage on education, we would obtain the sample regression of sample or estimated wage equals the estimated intercept and the estimated slope times education. Okay, and the beta 1 is here a biased estimator of the true population slope, since the error term is correlated with education, because the error term now contains the information that our that wages, or sorry, the error term contains both the effect on y by ability and the original unbiased and uncorrelated residuals. So what we have is that this covariance between education and residuals, the population residuals, from here, okay, from equation 3, it's equal to the covariance between education and the old uncorrelated residuals and the population slope of ability times the level of ability, right? And here we can say that correlation or covariance between education and V, the original residuals, it's 0, so it falls out of the covariance equation, and this beta 2 is a constant. It's the population coefficient, so it's a constant. So we can move that out of the covariance equation as well. So we are left with beta 2, the covariance between education and residuals is equal to the true population coefficient on ability times the covariance between education and ability. So here you can say that the covariance between education and ability is not equal to 0, because it is most likely that people with high ability also more easily get more education. Okay, and that would be you who are taking master's degrees, and probably you have high ability as well, right? So once we have established whether or not our estimates are biased, and remember, we can't observe this. So here the sample regression line is going through the data, right? It's going through the data, and this slope is the beta 1 hat. It's biased, but so might the beta naught hat be, the intercept, depending on the data, okay? Or sorry, depending on the data and the model. This is the y hat, okay, or the wage hat, okay? So remember that the beta 1 line could actually be down here. So it might be having a lower slope, right? Less steep slope, I mean. But now beta 1 is accounting for both education and the ability. So but what you observe is the estimated slope, right? You don't observe the true slope or the slope of the omitted variable. So here you have to think logically. You have to know your theory, and you have to know the theory behind in this case, what kind of results would we expect ability to have on wage, and what kind of correlation would we expect there to be between wage between education and ability. Okay, so you have to think about what would you expect of the correlation between the x variables, and what would you expect from the effect of the omitted x variable. What kind of slope would it have on the y variable? Would it be a positive effect or a negative effect? So so we would like to know how much bias there is, and to help us quantify the bias, then we could look at equation 1, and let rho xu represent the definition of the correlation between the x1 variable, the x1 variable, and the residuals. So suppose that the second and third least squares assumptions hold, so there is no problem, but The first does not, because there is a correlation between the x1 variable and the residuals. So then we can actually say that our obtained slope, the slope we can see, is actually equal to, in probability, this means that it's a limit in probability which means that if our sample size increases, then this result holds, okay, in the limit. So then we say that the slope that we can see, it's equal to the true slope times the correlation between the x1 variable and the residuals times the true standard deviation of the residuals divided by the true standard deviations of the x1 variable, x1 we can say. Okay, so what does that mean? Well, it means that the term here represents how much omitted variable bias we actually have between, it's really the difference between the observed slope and the true slope, right? So if the first least squares assumption holds, this term would go away because the correlation here between x1 and the residuals, the population residuals, would actually be 0. So 0 times something is 0, right? But what we have from this is that the omitted variable bias doesn't go away even if we increase the sample size. A wrong model is still wrong, even if you are more certain on its wrongness, right? So and the size of the bias depends on how large this term is, so you see that if the standard error of the residuals is large and the standard deviation of the x is low, then this increases in size, and the direction of the bias depends on the sign of the correlation. Okay, so if x is positively correlated with the residuals, as we had in the early example here, let's see if we, yeah, both are upward sloping, right? So they are positive. So in this case, you would have a positive bias, and you can see that because the beta 2 here is positive, which means that you would estimate, if you estimated this, you would estimate beta 2 plus beta 1, and you would believe it's beta 1, right? So beta hat would be the sum of beta 2 and beta 1, which means that you would believe beta 1 was really steep, but it's really not. Okay. Let's see. We were here. So the direction of the bias is quite important, because if the correlation between x1 and the residuals is negative, then the expectation of beta 1 hat is less than the population slope, right? In that respect, we say that beta 1 hat is downward biased. So this would mean that you would have this, and this would be the beta 1, the true beta, but you would find something smaller, right? Because the correlation between x1 and the population residuals, they are negative. And conversely, if the correlation between x1 and the residuals are positive, then you would probably find something something larger than the true slope, right? And you could have a negative true slope, but in your sample you find a positive slope because you forgot to include or couldn't include some important variables. Okay, so how do we know if our estimate is upward or downward biased? How it's the same as how do we know the direction or the sign of the correlation? So the sign of the correlation is actually determined by the product of the signs of the population slope of the x2 variable, which means that does the omitted variable have a positive or negative effect on y? In our case, x2 is the ability variable, which logically should have a positive effect on future wages or on wages. So and it's the product of the signs of the slope on the omitted variable and the sign of the correlation between those two variables. Okay. So if we look at the example, we found that the covariance between education and the residuals is the same as the slope of on ability times the covariance between education and ability. So in our case, the sign of the correlation between education and the residual is determined by the sign of beta 2 multiplied by the sign of the correlation. Okay, which means that if these two variables are positively correlated and ability has a positive effect on wage, then you would expect our estimate to be upward biased. See you next time.